Today I will explain the microanalysis. Most of you use EDS. How many of you use EDS? Can you just, yeah, so nobody is the first starter, yeah? Okay, so, what are the objectives for today? I will explain that there are different techniques that you can use for analytical observation and what you can get out of the EDS data to understand the generation of X-rays, where do they come from, and how does that affect the resolution, how we detect them, and different parameters that affect your acquisition, the sample considerations, and how is the spectrum processing and the matrix corrections, how are they done and what do they include. So what is microanalysis? This is the definition. So it's the identification of the chemical elements presented either within or on the surface of an object, and additionally how the atoms of the elements are arranged with respect to each other. And it can be qualitative or quantitative. And two most important considerations that you need to take into account is the spatial resolution, or the size of your object that you need to analyze, and the detection limit. So there are different techniques, and this is a sketch depending on the spatial resolution and the sensitivity. So not always EDS is the best. This is what I want to say. Where do we use EDS? In TM and in CEMM. So what do you need to think about before you start working on the EDS system is which elements do you have? You have light elements, and if you have peak overlapping. And what do you want to do? What do you want to have? Do you want to have a qualitative or quantitative analysis? So depending on that, the sample preparation is crucial. You need a flat surface for EDS. So what we offer in the CEMM group, if you have bulk, you need to polish it, you have to have a flat surface, and you go on the CEMM. And depending on the weight, the percent of your element, if you have trace amounts or if you have minor amounts and peak overlapping, you can choose EDS system, which we have on two of our microscopes, the fake field emission and the old one, and also the FIB, which is it's really small. Or you can choose VDS, which is also on the fake. If you have nanoparticles or thin films, you may choose the STEM unit, which has the EDS on the FIB, or you can use TM. So you can use EDS or ILS. And here are three TMs, so one on the Chemical Institute. So the EDS, now we're starting on the EDS, the Energy Dispersive X-ray Spectroscopy. These are the short abbreviations that can be used. What do you get? What's the output? You can get the spectrum, the map scan, line scan, qualitative results or quantitative results. What do you need to first understand is the electron specimen interactions, and where do you get the X-rays from? So you get the X-rays from the whole area, so the spatial resolution in the EDS is not really good. Yeah? So if you want to analyze really small amount of grains, you will have problems. Small grains. Small amount. So today I will explain how the characteristic X-rays are produced and the continuum X-rays, the Bremstein. So the Bremstein X-ray generation, when an incident electron goes to the atom near the core, it changes its direction and it loses the energy. And that excess of energy has to go somewhere, and it goes into the X-ray. And Kramer showed that the intensity of the X-ray is actually proportional to the Z and the energy that you're using. So this is how the X-rays are generated, but you get like a hump, like a whale shape, because you have problems that you have absorption of the low energy X-rays. So, as I said, according to Kramer, the X-rays are proportional to Z. So that means that heavier atoms will produce more than the lighter elements. So that's why you have two types of holders. You can have an aluminium or carbon holder. Because you don't want to, I'll show you the next slide. The characteristic X-rays are generated in a way that the incident electron from the beam takes out a core electron. It is replaced with another one from an outer shell, and that difference in the energy is produced by the difference in energy produces an X-ray. This was shown by Moseley. Before that, they didn't know that the Z influences anything. And this gives you that every atom has its own characteristic lines, and there are really the exact number, okay? And this is what you use in the EDS system, the characteristic line to determine that. So just how you write the K alpha or K beta. So if you have K alpha, you have from the K line, you kick out the electron, and from the L line, one gets replaced, and you have the alpha. If you have two okay. So if you have from the M line being replaced with the K line, you have the beta, and again, and this is just, you have different lines, okay? And now what is important, the EDS spectrum is a mixture of the continuum, the branch diode, and your characteristic lines, which are not really lines, they're broad peaks due to processing in the spectrum. And why you want to have a holder that has low Z? Because you don't want to have a high continuum. And why you don't coat material with other than carbon? Because you don't want to have high absorption in the upper layer. That's also the same. You want to see the peaks, not the X-ray intensity. Oh, and if you have any questions, just ask them now. If I don't explain something correctly or something like that, you don't have to wait till the end. The X-rays, here is important the concentration, the beam current or probe current or spot size, depending on the microscope, the accelerating voltage, fluorescent yield, and X-ray absorptions. So these are the parameters that you need to understand if you want to know what the EDS analysis does. So the concentration that we have, you can typically detect in the EDS in bulk material. If you have a flat surface, you can detect 1000 ppm, but this is like the limit, yeah? So it's really hard to get that. So you would go to VDS, it would be easier. The beam current is really good, but because you're increasing probe current, so the numbers of electrons, and that will increase your counts in the X-rays. You will produce more X-rays, yeah? And more X-rays will mean more statistics, better EDS spectrum. And the thing that you need to remember, if the relative height stay the same, if you don't have problems with your sample. So if you have a sample that is charging, then that won't be the proper way. The accelerating voltages used in the CEMM and the TM are different, and that also affects the EDS data, but also how the specimen is prepared. So in CEMM you have the bulk, you have low spatial resolution. In TM you have a thin layer, a thin film, thin foil, so you have higher resolution. The interesting part for me was, why does every EDS spectrum finishes at 20 eV? because the efficiency drop of the detector really drops. So if you go above 10 keV, the detector drops to 90% efficiency. If you go to above 20 keV, the detector drops to 50% efficiency. So that's why all the spectrum you can change from 0 to 10 or to 0 to 20 keV. Over voltage ratio is important because you need to excite the X-ray energies. You have here a sketch. If you put 5 keV on the beam, you won't, this sample is iron, you won't excite any X-rays. So you need to put a higher voltage. So the iron has 6.4, and if you put 15 keV, you will excite iron X-rays. Yeah. So the over voltage is important, and it should be between 1.5 and 3. But it affects your spatial resolution. If you have a higher voltage and you have lower spatial resolution, okay? Yeah. So also, if you're doing like a quantitative analysis, it affects. So this is a graph if you're using 15 or 25, because you're looking at the copper line and the silicon line, and the heights will change because the over voltage ratio for this one isn't enough if you're using 15, so you go higher. Yeah? So the X-ray production goes something like this, and then it drops a bit. So the optimum is 2.7. Okay, this is done by just the physics to how the ionization of the atoms. So it's a formula, so nothing special. Fluorescence yield, you have maybe heard of it, because you have a continuous process that you can produce. When you're ionizing your atom will relax. And how it will relax, you have a two-stage process which you have a competition between Auger electrons and continuum X-ray production. So we already have seen how the characteristic lines are done, and the Auger is the outer electron. What's the problem? That you have, for light elements, they tend to be relaxed more with Auger and heavier more with the X-ray emission. That's why it's harder to detect light elements, and also not only the relaxation process but also the absorption factor influences. So it's a competition. X-ray absorption. So this means that the X-ray that is generated somewhere in the sample, when it's coming out of the sample, can be absorbed in the matrix of your sample. So this is then this influences what you then detect on the EDS. Yeah. Okay. Now we're on. We will start to look at the detectors, how they are made, and what type of detectors we have. So the C detector, SDD. There's also a teardrop shape and one microcalorimeter, which was never produced. So the system is the X-ray detector, and you have the pulse processor. Then you have mix, which actually allows you to move the beam in point and ID. When you're using it, you're moving it with this one. And power supply, and you need a PC. Okay, so the EDS consists of a collimator that only lets in the X-rays that are parallel to the detector. An electron trap, because if you get any backscattered electrons in the detector, you can get a really your EDS isn't good, yeah. So you get a shift of the peaks on the right positions. a window because the whole detector is cooled, and if you didn't have a window, it will act like a cold finger. So we need to have a window. They are made out of the old ones from beryllium and the modern from the polymers. Semiconductor crystal, so silicon, and the electronics FET transistor that records the current. Yeah. So in the old ones you have a cryostat, and the new ones you have Peltier cooling. So what is the CEMM detector made out? So it's a lithium drifted silicon semiconductor. It's cooled, and this is a cross section. When an electron hits the silicon, when an X-ray hits the silicon, X-ray hits the silicon, it produces electron-hole pairs. So in the silicon detector, the energy is 3.8. So if you have a nickel K alpha line, you will produce almost 2,000 electron holes. And in alpha, you will produce 400. And if you would get like a backscattered electron here, you can imagine, yeah, two backscattered electrons, the error would be 1%. Yeah, the big sheet. So that's why you have to have a trap for the electrons. Yeah. So the animation, the X-ray goes in, produces electron hole pairs, and because you have a bias voltage, holes will go up, electrons will go to the anode, and there you will count them. And this is really good to understand, because if you get two electrons at the same time, two X-rays. Why am I? Two X-rays. Okay, I think you get it if I say it. Two X-rays in the detector, it won't be able to distinguish between them. So it will measure the sun peak. We will also talk about that. So the silicon drift detector, on the other hand, has a smaller anode. That's why it doesn't need cooling with liquid nitrogen. So the 40 degrees minus is enough, Peltier cooling. And you have anodes which are on different potentials. So when an X-ray comes, it depends on where it hits the detector. You will produce electron hole pairs the same way and the silly, but they will drift to the anode, and there you will count them. So it can distinguish between different X-rays. Yeah. So that's why it works faster. You get more counts. So it's better. The teardrop shape was invented because you have a small FET transistor here, anode, which you can damage because if you're using really high currents, you can burn the FET transistor. So a lot has been made to somehow move the anode, the FET transistor, and shield it so you don't burn it with X-rays. Yeah. So if you're using high currents, like in VDS and EBSD, and you're not going to do EDS, you just retract it. Yeah. So it's useful to do that. The microcalorimeter was really improvement in the 1998, because it showed that you can measure the X-rays with the same resolution as the VDS, but unfortunately you would need helium cooling, and it never made it to the market, but it's an interesting way how to detect the same way that we do now, EDS, so maybe something else will come up soon, so you get better resolution. Okay, this is the explanation of the process time, dead time, and tools pile up. So when I started here, there was like a saying, you always work on 25-30% dead time, and for me that was just like a why. Yeah. So how do I explain what does the production how does the production of X-ray happen? Yeah, so you get X-rays in the detector, yeah, and you need to count them. And imagine that you work in a factory, and you need, and the conveyor belt is going really fast, and you have some blocks you need to count. And if it's going really fast, you will have a higher error, so your peak shape will be Gaussian curve. So you need to count fast, yeah, like 10, okay, this is like 8, this is like, I don't know, 11, you will have a higher error. If it's going really slow, you can count them really properly. So you have a narrower peak, yeah? So this is how I explain it, but because I have time now, I can explain it what's really going on. When the peak, when the X-ray hits your detector, you get a pulse, yeah? And the process time means how much time you will give the processor to process. Do you have a lot of time? So process 6, long time, or process 1, do it really fast, yeah? So when an X-ray hits, you get a bump. And if you count them, this is the time, and then another one hits, and another one, and another one. So if you say, count them really, really fast, because I want to have all, count them really fast, you will get 1, 2, 3, 4, and let's say this one is also a pulse, 5 pulses, yeah? And you will count all of them, and no pulse will be left behind. So this here means dead time will be 0, because you're actually the time that you need to take into account is the error. So this is the I think does anybody get it in a way like that or no? Okay, so when the pulse comes, you say how long will I average my current, so the electrons. Yeah, if you average them, this is the process time. Really small, you will collect more counts. Yeah, so no dead time. Okay, but you have a higher error because statistically this is not long enough, so you have a broader peak. Okay, do you get it now? Okay. If you use process time 6, you will acquire a longer period of time. So in this case, here, you cannot take that much time. So this will be your dead pulse because it cannot process it. So the longer time means less of an error, a narrower peak. And here, if you say 5 counts, 5 X-rays came in, and you only process them 4, that's 20% dead time. Okay? Okay. So the process time and the resolution at that time at different process time 1, 2, and 6 for SDD don't differ that much. This is really important because on the silicity detector they did, and you should always use like 5 or 6 if you need narrow peaks. On the silicon drift detector, they don't. It's better, yeah. Okay, so why do you need to have 30% of the dead time? Because you need, so the good EDS analysis dead time, or more important, counts. You need a higher statistic. More counts, more statistic. So these are showing 2 graphs, the long process time and the short process time. What does that mean? And these are the counts, yeah? So if you're using the long process time, 6, this means that you can be, for the processor to work really good, you can be to about 50%, because you know if you have that time above 50, it will never end that position, yeah? So if you have 30 or 40, you will get the most counts out of your system, so better statistic. You can have lower dead time, not a problem, but then you will have less counts, so not that good of a statistic. Yeah? And if you use the short process time, you see that the graph really changes, so you get more counts because you can process them quicker, you have smaller. And again, it's better to be here than here because the statistic will be better, more counts. Okay, counting statistics, this is just to understand what's 1 sigma, 2 sigma, 3 sigma. 1 sigma, Gaussian curve, 2 sigma and 3 sigma ratio. And what you need to remember is that when you're labeling your peak, it's good to use 3 sigma above the background. So your height should be 3 sigma higher, so you can label it as a peak. Okay? And clearly, more counts, the better is your EDS precision, but not accuracy. Yeah? Okay, artifacts that can happen are the 3 main types. You have internal fluorescence peak, escape peaks, and some peaks. So in an internal fluorescent peak, when the X-ray is absorbed in the first silicon dead layer, so this is here, in the silicon dead layer called, this is the first layer, it won't produce any whole pairs. But it can produce a silicon K alpha line because it's made out of silicon, and the result will be a small peak silicon K alpha in the EDS. You can see that. The escape peak means that you get a silicon K alpha generated inside your detector, and it just gets out, so you won't get the electrons count, you won't count the electrons for that energy, so you have a shift of that energy, and this is shown here, but it's small, and the new programs, you have options that they reconstruct, and they will actually put out those problems. Yeah, so you can see this is the shift and a small amount, and if you don't know what you're doing, you could say this is another element, but it's actually not. The sum peak is really important if you have high dead time, because then you will have problems with 2 peaks coming at the same time, and you will count them as one. Yeah, so you have high count rate for E and B, and also you can have A plus B. So the X-ray comes at the same time for A, and another one for A, and in the CE detector, they will be counted as one, and you will say, this is another one. Yeah? And in Inca, this is corrected by a pulse pileup. Correct, pulse pileup. You have it. You You can check it. You will see on the next hour. Or I have it here. This is your spectrum, and if you uncheck pulse pileup, you will see that you actually got the sum spectrum, but the Inca is really smart, so it doesn't allow you to do stupid things. So it will say, this is a pulse, this is some peak of some other peak that you have. What do you need to think about the specimen, involving the specimen? So the absorption factor is important if you don't have a flat surface. So here you have higher absorption, and in quantitative analyzing, you wouldn't get a proper number, yeah? And if you have some inclusions inside here, also If they are from an element that has lower Z, you can get an absorption and you can emit those X-rays. So you also have a problem. And the homogeneity is the crucial thing, because EDS, when you're doing EDS, you are implying that you're doing when you're doing spot mode, you're implying you're doing on a homogeneous spot. So you don't know what's underneath. Is it a grain, or do you have some other, like a hole or something else? So we will later talk how to see if you have problems with homogeneity. So it must be homogeneous at the place of the analysis. What do you have? If your surface is charging, one time I came to the microscope and there was, you could see a huge charge, and the guy was still working on the microscope EDS, so I was like, okay, don't do it. Yeah, no, but it's working. Yeah, you're getting something out, but you don't know where you're getting it from. So if you have a high amount of charging, it will shift your beam, but you won't see that, because you will say start collecting and the charge will be built up there and it will shift the beam to another place and you will be collecting from that place. Yeah, okay, yeah, you get some numbers, but what? Or the other thing that's really important, you can reduce the landing voltage. So if you put 20 kV on the incident beam, because of the charge effect, you will have a reduction. You will have here if you have like a charge build up here, the minuses will slow down the electrons, and you will get 18 kVs landing voltage. Yeah, and we will also explain how the Inca can say, this is happening. So it can open a pop-up window, but I don't think anybody uses it. Okay, now the spectrum processing, the background subtraction and the peak fitting. So you need to remove the background because that's the Bremstein radiation. This can be done theoretically by following Kramer's law or applying mathematical models. So the top hat filter, just remove the background because that doesn't give you anything about the weight percent of your element that you need to analyze. Yeah? Raymond Castan was the inventor of EDS, started the EDS analysis. So he was doing his PhD in finding small inclusions of copper in aluminium for, I think, planes. Yeah? And he was working on this machine, and this was his prototype how to measure the X-rays. So his thesis led out to the basic of the EDS and BDS analysis. His first approximation was that you can measure the concentration of your unknown sample, of your known sample, depending on your unknown sample, if you are if you're comparing the intensity of the X-rays, yeah, of the unknown and known and unknown sample. Okay, so these are the first. So he had the K ratio. So why is that really important? Because it cancels its other parameters out. So if you're using on the same instrument and on the same condition, they cancel other parameters of the machine. So that's why you can have the K factors. But is that really all on the CEMM? Yeah? Here are 3 alloys, iron, and this is the EDS measurement. So the red one is iron nickel, and then you have the blue one, iron chrome. So if you look at the 40% of iron, you can see that you have the intensity change. You have the changes in the intensity. Why is that? Because you have the secondary fluorescence. So an X-ray is absorbed in your matrix, and it can produce another X-ray. Yeah? Okay, do you get it or no? Yeah. Okay. So you have iron, you have chromium and nickel. So chromium has a lower energy. That means that when you, from the incident electron beam, excite the iron, you will produce an X-ray of iron, and around, if you have a chrome matrix, that will be absorbed in that matrix and produce a chrome X-ray. Okay? So in this case, you will have a detection on your EDS lower for iron, but okay? And the same for nickel. It has higher number, so you will see more iron than it actually has. Okay, and these are the matrix corrections, SAF corrections, or Firose, yeah? So in the CEMM, you need to take into account the matrix effect. Oops. Okay, this is an article by Heinrich, where he really explains the basic how different why we use different methods and everything. And he puts it into 4 branches. So the empirical, where you have alpha corrections, which we don't use anymore. The ZAF correction, so I will explain that later on. Firose, based upon measuring trace elements, and the Monte Carlo simulations. Yeah. So on the Inca, we use the Firose models. The ZAF corrections, so the Z is the atomic number, so it describes how the stopping and the penetration of your electron. Yeah? The A for absorption, it takes into account the X-ray absorption along the path to the detection. And the fluorescence, so the secondary fluorescence will give you a different EDS. You need to know what's around your place where you're taking the EDS. Yeah. As I explained on the other graph. Yeah. So the ZAF quant, or the same as on the Firose quant, when you're doing a ZAF correction, how is it done? You're measuring the intensity, calculating the concentration without ZAF, and you get the concentration, and then you calculate with the ZAF correction twice, and then you compare both of them. If they are matching in 1 sigma, or depending on what you put on the microscope, usually 1 sigma, you stop. If not, you correct the ZAF, you again calculate, and that's an iterative process. Commercial correction models. So the ZAF correction were replaced by the Firose models. And you will, so the Firose, or what's the phi? That's the phi is the takeoff, so the angle. The rho is the density, and the z is the density. So the density, and the z is the Robina. Depth. Thank you. Okay, so you will hear 4 different names: Proza, PAP, XPAP, or XP. So we have on our 2 SEM, on our SEM and on the FIP, you have XPAP, so extended Pouchet and Bourgeois. So they calculate them, and then Oxford bought this too. Yeah? If you're using Kamika or something else, you will use a different one. You also have correction models in TM, so the K factor, as I explained last time, correction factors, the new Cliff Lorimer factors that you have on the TM, or the better ones, zeta factor, where you measure the beam, or you can use Monte Carlo simulation. So these are the software that you can use. They're all available on those websites. And I finished on time. Do you have any questions?
At the beginning you mentioned two types of holders. Whether I would use this carbon holder.
Yeah, so carbon has lower Z than aluminium, so if you know you will be doing EDS, you will immediately go on the carbon one. But sometimes they are both good, yeah, so when do I use it? If I know I'm detecting aluminium particles, then you need to have a carbon holder. So, but it's better to use an aluminium carbon holder anyways because it lowers Z. Yes.
As I understand, if we have powder and doing EDS on the powder, we cannot get the correct quantification. Or am I wrong? So,
yeah.
But what's the error? Like 5% or something? Because for me, it's really important if I have 25 or 20% of some element inside.
Yeah. So in the next workshop, we will talk about how to determine the error. In particles, you have a really it depends on the operator. So you need to take account. I mean, really, no. You just don't click on every particle, but you need to know how are the particles, where are they? Do you have any humps around? How the surface needs to be flatter. If it's tilted, you will have more production of X-ray. It really, I mean.
So I should search for the highest particle.
Yeah, for the highest, because if you have a holder and if you have particles, and maybe you will have some particles here and detector here, yeah, you will have absorption here. And also, if you're analyzing on top, okay, if you're analyzing here, a problem, not here, but like here, you click, you can see. So the area where you're analyzing is important, and then you need to have more, like if you're doing point and ID, more point and ID spectrums and compare them in Inca, because it can be you can see how they differ, and then you just take the one that's the spectrums that are more closely together. That's statistical. So better way is to go on the stem, because you will put particles on your carbon. So not stem, TM, but stem on SEM. So you put on particles on the grid, and you don't have high energies. You have the same as in SEM. So the interaction volume will be the same, but you won't get anything from here, because if you're having small particles, you only get a small amount of X-ray depending on what's underneath that, and that's also a problem. You know, if you have particles, also this could be a problem. If you have like 2 particles, or if you have a bunch of them, yeah? Because the amount of X-ray from here and from your sample, and the amount of X-rays here.
So this is a special folder. What should I use for this? It's a special
yeah,
folder.
You could use, I mean, in this case you would always use the carbon holder, but this is STEM, this is a different unit. We want to have it on our new microscope, but
so we don't have it yet.
It's on film. But you also have lower counts here. So, but if you have nanoparticle STEM or TM, it's better.
Okay, thank you.
About the Monte Carlo, what type of information we can obtain from Monte Carlo? I performed some simulations in which I could see the penetration depth depending on the Z value. What other information we can obtain?
You can take anything. Monte Carlo just means a method where you're putting random numbers and how many iteration it will do. So you can put if you have thin layers, nanoparticles, something like that. So you can simulate, if I have a thin layer of that, a thin layer of that, how much X-rays will I get from that? How will the absorption factor interfere? If you have a non-homogeneous sample, how would that affect? Monte Carlo is also good if you have a tilted sample. If you're tilting samples, then you will see how does the influence between the generated X-rays and the X-rays that you measure come into account. So it depends on which method you. I mean, I only know about this casino, so I don't know actually about this one what it does, but here you can do like I don't know, nanoparticles and put them and then see how the X-ray are, just to see if it.
So at the end of the day, you get the depth where the X-rays are coming out. The interaction of the electrons with the material itself. Yeah?
Not only the interaction, but also you can check the overall voltage ratio, because in Monte Carlo it's really easy just to see, if I put 5 keV and you put what your sample is, it will say you won't get anything from that, you won't get anything from that, but your spatial resolution will change. So it can give you, the people who are really working on the EDS first do the Monte Carlo simulations and see the conditions, and then go on the microscope. So it gives you.
Okay. Can I ask one more? In which conditions it is necessary to do the standard EDS analysis? Under what conditions? What are the
Standard conditions? Yeah. So the standard conditions on the old microscopes are 20 keV. If you don't have your own samples. On the new microscope, so the Inca, if you see a denotation standard 1999, it means it's a virtual standard. So it's not a pre-recorded standard. And you can use any proper parameters because it's based on the simulation. So on the old ones, they were collecting standards. But we will have that in the next. Okay, so now you can take the biscuits and stuff like that.